All right, now that we have looked at what happens when you have uncoded modulation over fading channels, I want to turn to looking at coded communication over fading channels. I'll first start with a little bit of a theoretical perspective on this to understand theoretically what are the gains and when you can get them, and then we're going to look at how to actually build real channel coding systems after this. So let's start with that. So the lesson from that previous section was that with fading, uncoded modulation is very difficult to provide sufficient reliability. Just as a quick recap of that graph we saw, this was the error rate on I think a 16 Comm constellation, and we see that without fading it decays very quickly, but with fading it decays very, very slowly, meaning that you have to add a large amount of SNR to try to get a sufficient level of reliability. So channel coding is one possible way of doing much better on these fading channels. The key idea is that you send data in blocks. That means in groups of bits, and these blocks contain redundancy. That means that if some parts of that coding block fail, you can still recover from other parts of the blocks. And virtually every commercial wireless system, for this reason, uses channel coding. All right, before we analyze how channel coding works over a fading channel, we need to review some concepts of fading. So recall that channels vary over time and frequency. Remember that they are characterized by a time-varying frequency response. So just as an illustration, I created the time-varying frequency response for some synthetic channel with about 20 paths, and the Doppler spread is 100 hertz, and the delay spread is about 100 nanoseconds. And you can see if I plot the SNR of that channel, it will vary indeed over frequency, and it will vary in time. Now, the variations in time, remember, are due to the Doppler spread. That is due to the velocity of the receiver or the transmitter relative to the paths. And with that, you get something called the coherence time, which is roughly the inverse of that Doppler spread. The coherence time in this case would be about 5 milliseconds. That is 1 over 2 times 100 hertz. And you can see that indeed within this time the channel does, after you pass through about 5 milliseconds, the channel can vary significantly. So if you want it to be constant, you have to be much smaller than the coherence time. Similarly, you have a variation in the frequency, and that is due to the delay spread of the different paths. And that coherence is characterized by the coherence bandwidth, which again is 1 over 2 times the delay spread. And that is roughly the frequency distance you would have to travel before the channel becomes uncorrelated in frequency. All right, with that in mind, we can think about what happens with coding. So when you transmit a coded block, it will occupy some time by frequency resource, if you like. So in this visual representation, you can think of it like a block with the vertical axis being the frequency extent of that coded transmission, and the horizontal axis being the time extent of that transmission. Now, when you have this, there are two possibilities. One is what you could call flat fading. In flat fading, the block is very narrow in this frequency dimension. And the consequence of that is that the channel in frequency will be basically flat or constant. It can still vary in time, depending on the length of the block, but we'll just refer to flatness by the thickness of this block in frequency. And it will particularly be flat when the thickness of this block or the frequency extent of that transmission is much smaller than the coherence time. In contrast, the opposite of that is what we would call frequency selective fading. Once that block gets to around the order of the coherence time, you'll see a significant amount of variation, and it will no longer be constant over this frequency region. And that will apply whether the block is long or short in time. Now, just like you had flat versus frequency selective fading, you can also do the same in time. So again, you have a block, which is W by T in frequency by time. And we can think of what we would call slow fading. And that is that the time of the transmission is very small relative to the coherence time. So it doesn't change much in time. It can be very long in frequency. But what matters here is just this dimension. Or what you would call fast fading. Fast fading meaning that it has very long, it becomes comparable at least to the coherence time. So there would be a significant variation of that channel over that coded transmission. And when you put that together, you really have four possibilities, depending on the frequency and time extent of the block. So there are these two dimensions I've drawn here, the frequency on the y-axis and the time on the x-axis. When the time gets larger than the coherence time, it will go transition from slow to fast. And when it gets wider in frequency, it will transition from flat to frequency selective. And hence getting four possible options depending on the shape of that block, that coding block, relative to the coherence and bandwidth and coherence time. Now, to analyze coded transmission, I'm going to take a look at two kind of what you could say are extreme cases. The first case is the case where you're in this lower left-hand quadrant, meaning it's slow and flat. This will be an easy case to analyze because in this case, I'm just going to approximate the channel as basically flat and slowly fading, hence roughly constant over that coded block. The second case I'm going to analyze, which I've drawn in these green squares here, is kind of the other extreme, where it's either so wide in frequency or so long in time, either or both. You could think of the channel as having many independent fades across that fading block. The specific mathematical model, the one we'll call is IID fading in that block. So let's start with the first, easy to analyze, which is the case of flat and slow fading. So in this case, visually, you can think of transmitting a very small block relative to the variations in frequency, i.e. relative to the coherence bandwidth, and very short relative to the coherence time. So in this case, that coding block would see some SNR, let's call it gamma, and that SNR may vary over time in frequency, but within that block, we can consider it constant, just like I've shown here, meaning the transmission time is much smaller than the coherence time, and the transmission bandwidth is much smaller than the coherence bandwidth. Now, suppose that code, and this will depend on the modulation and coding scheme that you pick, has some target SNR, call it gamma target. And that would be dependent on the MCS. It would also depend on whatever reliability, like the block error rate probability. Now, over this time frequency full region, gamma would be a random variable. And depending on when you transmit this, this could fail or not fail depending on the particular gamma you see. And that leads us to what you could call is the outage probability. The probability that this coded block will fail depending on which particular gamma it sees. Or, in other words, you can think of it the fraction of time that that block would pass. Let's just do a simple example. Suppose channel is Rayleigh fading, and that means that the SNR is going to be exponentially distributed around some average value, which I'll call gamma bar. So the outage probability in this case would just be the probability that the SNR you see is less than the target, but since it's an exponential, it's given by this simple exponential formula. Now, we can just rewrite this value here to solve for gamma bar. And that would mean that the average SNR to get a certain outage probability is just given by this expression here, the gamma target on the top. Now, one way to think about this is the following. Let's take a look at the ratio of the average SNR that you would need relative to the target SNR. That's kind of, you could think of it like an additional amount of SNR that you would need to make sure that you get a certain level of reliability. If you just put that in and plug that in to this and solve it, you get that value for small values of the outage values about 1 over P out. or equivalently in dB, the average SNR has to be equal to the target area, target probability, minus this factor. But since P out is a number less than 1, this is a positive value. Let's do a simple example so you can see how much that extra fade margin would have to be. Let's say that your target SNR is about 10 dB, and you want to make sure that you can get that 99% of the time, which is not really that reliable by wireless systems, because remember, they're carrying data, and pretty much every error is going to have some detrimental effect. So we want to get 10 dB at least 99% of the time. All right, from that previous slide, we would need that the average SNR has to be 10 plus this factor, but in this case, this is easy to work out because it's log base 10. You would need another 20 dB, or in other words, that the average SNR would have to be 30 dB. Just the way you can think about it graphically if you prefer, call the fade the actual value of the value gamma relative to its average. So this would be an exponential random variable. So if I draw its complementary CDF, you would get this kind of expression here, which means that if you want to guarantee that the fade is within 1%, you have to look at the 1% possible value this could be, and that would be 20 dB. And if you wanted to guarantee to say 99.9%, you would have to add on an additional 30 dB. So the implication is that you have to put on 20 dB above the target, right? And that means that you have to add a very large fade margin. The average SNR is 30 dB in this case, but you can only reliably send at a rate that's compatible with 10 dB. Now, another way you can think about this, if you prefer, is what you could call outage capacity. So suppose that we can achieve some rate as a function of the SNR, but the SNR is random, so the rate will be random. And then I could say, well, if I have a target rate, if you like, I can look at what's the probability of that rate. Just as an example, suppose that the system is 20 megahertz of bandwidth, and you get 60% of Shannon capacity. It's kind of pretty close to what happens in an LTE or a 5G NR system up to a certain spectral efficiency. All right, and let's say that the average SNR is 20 dB. And then I ask you the question, what's the outage capacity for 1% outage, assuming rarely fading? Well, just like before, well, you know that the average SNR is 20 dB. With a 1% outage, you have to basically add on another 20 dB. So you can only assume that you're going to get 20 minus 20, or 0 dB with 99% probability. So take that 0 dB, convert it to linear scale, and let's put it into Shannon's formula. This is the 0.6 from my assumption that we're 60% of Shannon capacity, 20 for the bandwidth, and log of 1 plus the SNR, and you get 12 megabits per second. Just as a comparison, if you could actually signal at the average rate, you put in the 20, which in linear scale is 100, and you would have gotten 80 megabits per second. So on average, this channel can actually transmit, has a capacity of 80 megabits per second. But just to be reliable, and not even that reliable, you have to go all the way down to 12 megabits per second. So you're getting a tiny fraction of what you could get. So what are the implications? If you have both flat and slow Rayleigh fading, you will have to add a very large fade margin to try to get reliable communication. And one of the implications here is that channel coding is not really fundamentally mitigating fading. And that makes sense because the fading is causing all bits to fail. So it's not like you can actually benefit from the redundancy for mitigating fading. Of course, you still will want to add channel coding because it will allow you to average out effect of noise, which is random across the coding block, but it doesn't get you around this fading problem. Now, this is clearly an issue, but there are potential solutions even if you have to transmit over with flat and slow fading. For example, if there's motion, perhaps the channel will be better at a later time. and then we could retransmit later. Or maybe we can just adapt the rate somehow to go to a lower rate. Or perhaps in some applications, we could just accept that there are going to be some locations that are in outage. In the next unit, I'm going to go over some of these MAC layer principles that will allow you to get over this. So do not despair if your system is in this situation, but just understand that coding by itself is not going to get you out of it. Now let's go to the next extreme case. And this is what I'm thinking of with coding blocks that are either fast or frequency selective. So I've drawn a few examples here. In this case, I've drawn a block that maybe doesn't have much variation in time, but has a lot of variation in frequency. Or maybe it has a lot of variation in time, but not very much variation in frequency, or both. Any of these cases, coding is going to do some good, as I'm going to show. Now, in this case, we have a lot of variation across the coding block. Just to analyze this, let's take a kind of extreme mathematical model for this. And this is not exactly correct, but it'll actually give you pretty close to predictions once you get into the mode where you either have a very wide frequency extent or a very wide time extent. So this is the model. I transmit some symbols S of n, and n here is an index of some degree of freedom, which could be a time or frequency. For example, if it was OFDM, that could be some time frequency resource element. Each of these symbols experiences a channel gain, which I'm going to call h of n. And the key assumption here is that h of n I'm going to assume is IID. So basically I get a large number of independent fades. And I get some noise and I get this received symbol. And I've normalized these values here. So this is our SNR, which I'll call gamma sub s. That will be the symbol SNR on that particular degree of freedom. Again, just to make this simple, I'm going to assume I have a large number of symbols, or equivalently a large number of degrees of freedom in that transmission. So just from a physical standpoint, what this means is that I'm coding over a very long time or frequency block is sufficiently large relative to either the control or the coherence bandwidth or the coherence time to experience a large number of independent fades. All right, with this kind of very abstract mathematical model, let's try to analyze what is the theoretical capacity we could get. This relates to some concept called the ergodic capacity. So again, just to refresh, our model is we're seeing n symbols, and with each with these IID fades, h of n. What we could define is something called the ergodic capacity, which is very similar to the capacity that you think of in information theory, which is meaning this, that from a theoretical perspective, what is the maximum rate per symbol I could transmit? And I'm just going to assume that on average, I have some energy constraint on the symbols. And right now, I'm just going to take the maximum of all possible codes and all possible block lengths without any computational limits. So clearly, this is just a theoretical calculation, but it'll give some idea, as I'll show you, about practical systems later on. The key theorem is the following. It's super easy. So the ergodic capacity, when you're in this IID theoretical universe, is given by the expectation of this expression. You will recognize that the inside of this expression is none other than the Shannon capacity for a given SNR, and you're just averaging over that. So it's the same capacity as if somehow you could transmit in each one of these fading realizations and then average that capacity. I've put the bandwidth expression here, so you think of this as the capacity per symbol, or the capacity per degree of freedom. If you have, you have to multiply that by that number of degrees of freedom to get the actual number of bits that could be transmitted in this coding block. All right, I just want to talk a little bit about some notes on this expression. So here's our expression from the previous slide. The first thing to understand is that it's a theoretical result. Principle to get this, you would need an infinite amount of computation and an infinite amount of delay. So you'd really want ideally this block to be either very long in time or very long in frequency, or very wide in frequency. But I'm going to show you next, if you look at these state-of-the-art remarkable codes that people have developed, you will actually get pretty close to this performance at practical block lengths with a reasonable computation. All right, the next thing about this is that the transmitter doesn't even need to know the h of this, but the receiver does, and that will be critical. We're going to talk about that when we get to equalization, but the transmitter doesn't need to know it. Now, it turns out that if the transmitter did know, you could actually get even a little better by playing some games. Specifically, what you would do is you would try to optimize your power distribution to put more power on symbols which have higher SNR and less power, or maybe even zero power, on symbols that have lower SNR. This trick is called water filling. It turns out that that optimization in most practical scenarios doesn't get you much bang for your buck, so I'm not going to cover it in here, but go ahead and check out the textbooks because they do give it if you want to get the theoretical result. All right, I just want to quickly compare the ergodic and flat capacity. Just to understand that, I'm going to say that the capacity with fading for any distribution will be always lower than the flat and slow fading case, assuming that you're keeping the average SNR constant. This is just a simple consequence of what's called Jensen's inequality. Because remember that the capacity is the expectation of this logarithm, but because this is a concave function, you can upper bound it by bringing the expectation inside. So then you have the capacity of a channel with that average SNR. So if you call that the AWGN capacity, you see that the capacity with fading is always going to be less than or equal to flat fading. So in other words, the capacity is always decreased when you add fading. But the capacity is not decreased by that much. Just take a look here to just plot this. So in this case, I've looked at some SNR ranges from about -5 to about 10 dB. And I've plotted the AWGN capacity from Shannon's formula. And I've also plotted the capacity under Rayleigh fading with that same average SNR. Indeed, the red line is lower than the blue line, but it's not by that much. Lots of SNRs, for example, say that you're looking at a spectral efficiency of about 2 bits per second per hertz, you're only losing about 1 to 2 dB. So the consequence of this is that you should definitely try, if possible, to code over a large number of fading realizations, either in time or in frequency. At least theoretically then, the capacity loss should be small and will do a lot better than coded modulation. And in fact, we're going to see that with some practical codes, given how advanced these codes are today, you can get actually a lot of benefits with these codes. All right, one final thing I want to emphasize when thinking about capacity is the following. Up to now, we've really been talking essentially about variations due to small scale fading. That is variations from the constructive or destructive interference of these multipath components as you vary either the frequency or your spatial position. All right? And these may or may not vary within the coding block depending on the size, time, or frequency of that coding block. But just physically, this means is following. Suppose I had like a room or office like this, right? Those variations could happen in a very small spatial area, or even in a particular point could happen over frequency. But of course, in an area like an office like this, you would also experience what you could call large-scale fading. These would be variations to all sorts of other parameters, like the distance you are from this access point, or shadowing, say, from the walls, or angles of arrival relative to the directivity of your antenna, and so on. Typically, though, these always occur at a much slower timescales, at least in the hundreds of milliseconds for most of these phenomena, if not much, much longer. So they rarely vary over a coding block, which is typically at most around in the tens of milliseconds. So for example, if you're looking in this region, as you move here, maybe within a room, you could see this variation as you can, is predicted by, for example, this ray tracing here, but this would occur much slower relative to the coded transmission. Now, just when you're trying to analyze this mathematically, the way you can think about it is like this. You have an SNR, which is really dependent on two parameters. Call U, which is a vector of all the large-scale parameters. So this could be distances, angles, shadowing, and so on. And that varies slowly. And then we could say there's a vector V with all the small-scale parameters. And for example, the time scale, frequency, location of a particular degree of freedom. Now, if your fading in each coding block is slow and flat, you're basically experiencing an SNR that varies over both U and V. So if you wanted, for example, to compute the outage probability, you would compute a probability that SNR is below a target, taking into account that randomness in both the large and small scale parameters. On the other hand, if the fading in the coding block can be modeled as a large number of IID samples, it's going to be the IID samples only the small scale parameters. Obviously, the large scale parameters will very rarely vary over a coding block. So its ergodic capacity in this case could be looked at as an expectation of the log of the 1 plus SNR, but you only want to take the expectation over the small scale parameters. Your rate will still be a function of the large scale. For example, in that picture I showed on the previous slide, it would still be a function of where you are in that office area. All right, and then you could compute, for example, the rate CDF or the probability that the rate is below a certain target. Just as an example, I did the following little picture, and you can check out the demo, which I've put on the GitHub site here. Let's say you had a very simple mathematical large-scale model, and the SNR varies, where the average large-scale variation is given by some formula. And we'll just say that there's only one parameter for the large-scale variation, and that's simply your distance as a transmitter. So I've given some kind of square loss model. This is a very simple model. It's not that realistic, is just for the purpose of illustration. All right, and it has some average SNR and some reference distance where you get the average. Superimposed upon that is small-scale fading. So let's say that it was Rayleigh at each location. That means that the SNR you would experience is the average times an exponential random variable, which is related to that small-scale variability. So you could then plot the spectral efficiency under a constant model. That means that you're basically seeing a small, slow, and flat fading case where you're getting the variability both due to the distances where you are along with the fading V. You can see that's a very large possible variation. On the other hand, if you have a spectral efficiency under the IID fading model, so you're still seeing a constant D distance within each coding block, but you're getting many random realizations of the fading, you will get this red curve. You can check out the demo, and it shows you how to compute all of this in MATLAB, and it's very easy. The point, though, in this case, of course, you have much less variation because you're averaging out that this small-scale fading. In particular, if you had to plan for this, it would be much easier to guarantee a target rate because you can see that with the fading, there's a very high probability of a very low SNR. All right, with that in mind, I'm going to make you do a very similar calculation in a more realistic indoor environment. In this case, I take a path loss model from 3GPP, and I'm going to make you compute both the variation just due to the large-scale variation as well as the large and small-scale variation. So give that a shot, and once you work that out, you can go on to the next section.